In Section 8.2 and Section 8.3, which I'm going to kind of combine in a little bit, we talk about some properties that are existing for relations. And here are the three main properties we're going to talk about when we deal with a relation on set A. The first property is what's called reflexive. And it's reflexive if for every element in the set, X is going to relate to X. In other words, we could say in everyday language that something is going to relate to itself. The second property is symmetric. And the relation is symmetric if for every two elements, and they don't have to be distinct, but for every two elements you choose in the set, if X relates to Y, that implies that Y relates to X. The third property is transitive. That says if we were to choose three, and they don't have to be unique, three elements in the set A, if X relates to Y, Y relates to Z, that implies that X relates to Z. These three properties can go a long way in describing how a relation works on a set. And if a set has all three of these properties, a definition we'll learn at Section 8.3 is it's called an equivalence relation. So relations are called equivalence relations if they are reflexive, symmetric, and transitive. Now let's see what these things translate into when you looked at the directed graph of a relation. Here I've got elements A, B, C, D, E, and F. Right now I have no ordered pairs here where anything is associated with anything else. If I make A relate to A, I would draw an arrow this way. And that says A relates to A. If every one of these elements related to themselves, we would have a circle coming back on each one. And now, when I have that property for every element, we can say this is the first property of being reflexive. So the way you identify something as reflexive by looking at the directed graph is to see that every one of the elements has a circle coming back to itself. Symmetric says if A relates to B, B relates to A. So here we have symmetry. It means the arrow goes both directions. It doesn't really matter to me whether you want to draw two arrows or you want to draw one arrow with two different arrowheads. Now, it simply says that if it relates one way to the other, then it's going to be symmetric. Right now, the only situation where we have A relating to B and B relating to A is here, so this entire thing is symmetric. If I added in one arrow here, it is no longer symmetric because D relates to F, but F does not relate to D. And F not relating to D is our counterexample to show it's not symmetric. To complete having symmetry, I would have to have an arrow going this way. And now it's symmetric again. The third property is transitive, and it says if A relates to B and B relates to A has to relate to A. Oh, you see, I did that as sort of a special case there. So you see, this one is transitive here, and it's transitive here. And if I didn't have the reflexive property on A, or the reflexive property on B, or on D, or on F, I wouldn't be able to have the transitive property. Let's add in some other things. Since I drew the arrow going both directions, we still have symmetry. It's still a symmetric relation. But now D goes to F and F goes to E, but D does not go to E. So this one is not transitive. And it's not until we add in that arrow and this arrow that we have the transitive property restored. Putting in those last arrows is sometimes what's called closing the transitivity, and the set of things that we needed to get to that closure is what's called the set of transitive closure. Let's look at some other sets and see if they have these different properties. Okay, I have drawn here a relation with A going to A, B going to B, and C going to C, and C going to B. Since every one of these relates to itself, it is reflexive. It is not, however, symmetric, because C goes to B, but B doesn't go to C, so it's not symmetric. Is it transitive? Well, for every situation where C goes to B, B goes to itself, so that seems to work there. But, so it says if. Remember that symmetric and transitive are both if-then statements. There is no relationship between A going to B, so we don't have to look for a relationship for going B to A for symmetry. With the transitive property here, you notice that C does relate to C, and C does relate to B. Now you have to ask, does C relate to B? It does. You'll notice also that C relates to B, and B relates to B, and C relates to B. So guess what? This one is transitive. Let's look at the next one. A goes to B, B goes to C. Is it reflexive? No way. That's because we don't see the little circles going back on each one. A does not relate to A. Is it symmetric? A relates to B, B relates to A. Yeah, that one's symmetric. Is it transitive? Well, at first you might look at that and go, oh, I don't see any examples where it's transitive, but how about if we do this? A relates to B, B relates to A. Wouldn't that have to imply that A relates to A? Oh, but that doesn't work because we don't have the reflexive property, so this one is not transitive. Look at this one. Is it reflexive? That's pretty easy to see that it's no, because nothing is circling back on itself. Is it symmetric? No. A goes to B, but B doesn't go to A. Is it transitive? A goes to B, B goes to C. Does A go to C? No. So that has none of the properties. But before doing this one, I changed it up a little bit to make it a better example. Is this one reflexive? Well, A relates to A, B relates to B, C relates to C, but D doesn't relate to itself, so it's not reflexive. Is it symmetric? For every instance where A goes to B, does B go to A? Well, it does there, but B goes to C, and C does not go to B, so it's not symmetric. How about transitive? Well, let's see. A goes to B, B goes to C, and A goes to C. Notice that one. A relates to B, B relates to C. That would imply A relates to C, and that does happen. Also notice up here, A relates to B, B relates to A. That says A relates to A, and we do have a reflexive property within A itself, so we're okay there, and the same thing works out for B. How about B goes to A goes to C, B goes to C. That works. So this one's kind of interesting in that it does have the transitive property. Now let's look at something different. Something that has an algebraic expression. Like x is greater than y. Is this, for all of the real numbers, reflexive? No, no number can be greater than itself. Is it symmetric? In other words, it's looking at if 2 is greater than 1, does that imply that 1 is greater than 2? No, there's a counterexample here. But is it transitive? If A is greater than B, and B is greater than C, does that say that A is greater than C? Well, if this is to the right of B on the number line, and this is to the right of C on the number line, A has got to be to the right of C on the number line. So there's an example of something that is transitive without having the other two properties. Finally, down here I have x equals to y. Is everything equal to itself? Yes. If A is equal to B, is B equal to A? Yes. And if A is equal to B and B is equal to C, does that mean A is equal to C? Yes. Since it has all three of these properties, this is called an equivalence relation. EQUIL, equivalence relation. And this is why it's basically called an equivalence relation. It has all of the properties of being equals. Equals is the ultimate equivalence relation. We'll see when we get into the next chapter that there are others.